Hello, and welcome. I'm your host, Mr. McMahon. Today we're going to get into some actual trigonometry and applications of this stuff to, real-world stuff. Stuff you would see in engineering, in physics, maybe even in architecture. So let's go ahead and jump right in. The first thing we need to clarify is some terminology, right? So you have to get these terms straight before you can actually do any trigonometry. Whenever you have any sort of triangle, let's say it's in a word problem, real world situation, you want to first probably start by locating the side across from the 90-degree angle. Right? So, we have these 90 degrees here. If you imagine those angles sort of looking out across from themselves, right? Or like this. Or like this, the side they're looking out across to is what we call the hypotenuse. Right, most of you guys probably know that. Right, and I'll just label it with an H over here and here. And I label that first so that there's no confusion about what we call one of the other sides. Right, so you'll see that in a bit. The next side that I usually focus on is the side across from theta, right? So here's theta. The side across from that, we call that the opposite side, right? Because it's opposite of the angle, right? It's the side not touching the angle at all across from it, right? So in this case, it would be this side down here. We got this side over here, right? I'll just label them with an O. And then last but not least, right, we have that third side. That third side is what we call the adjacent side. Adjacent essentially just means next to, right? So this is the side that is next to our angle. So I'll label that with an A, an A. And this might seem a little tedious or kind of trivial or whatever you think about it, but if you get any of these sides confused, you will get the wrong answer guaranteed. Right? So if I give you any triangle in the future, you need to know exactly which is opposite, hypotenuse, adjacent. And you should not, have any confusion about which is which. Right? So you want to get good at this stuff. And for a foolproof method of labeling your sides, what I do is I always label the hypotenuse first because that's guaranteed. It's always across from the 90-degree angle. Then the opposite. And then if you end with the adjacent, right, you don't need to think about which side is next to the angle, right? Because technically this side is also next to the angle as well as this side, but we already labeled it as the hypotenuse. So that's why I sort of do it in that order, right? Makes it pretty much foolproof. So anyway, here are some other alternative definitions to sine, cosine, cosecant, secant, tangent, cotangent. These are the definitions that your previous teachers probably showed you. Right? These definitions are in terms of these sides to the triangle. And they come from, of course, if you've seen this before, right? SOHCAHTOA. Right? That's just sort of this little acronym that people commonly learn in school where the S, right, this is for your sine, the C, that's for your cosine, the T, that's for your tangent, and the two letters following tell you what two sides you take the ratio of. So sine, SOH, that means sine is the ratio of the opposite over the hypotenuse. Cosine, you got AH, right? So that's adjacent over hypotenuse. And then tangent, OA, that's opposite over adjacent. And the other three remaining trig functions you can figure out from sine, cosine, and tangent because they're just the reciprocals, right? So remember, cosecant is the reciprocal, right? The reciprocal of sine of theta. So if sine of theta is O over H, this one will be H over O. secant is the reciprocal of cosine of theta. If cosine is a over h, this is h over a. And then, of course, cotangent is just going to be the reciprocal of tangent, right? A over O, adjacent over opposite. And so these are the SOHCAHTOA definitions of sine, cosine, and tangent. And these are perfectly fine. If you want to think of these functions in terms of only SOHCAHTOA instead of the way I taught it before with the unit circle, that's completely fine. Speaking of the unit circle, I want to show you guys a really nice connection here. Right, so we did see earlier from the previous lesson that sine, cosine, and tangent are defined this way. Right, we essentially created a line going out from the center, and we found a point at the edge of our unit circle. And what we discovered was it creates a little triangle. Right, so we have this point x comma y, and we saw that x, right, this distance basically, is cosine of theta. And we also saw that this distance over here is sine of theta. Now, if you notice, we also, of course, because this hypotenuse is the radius of the unit circle, it's got to have a length of 1. And this is a right triangle. Now, if you know that, you can already get a free trigonometric identity without really doing hardly any work. As long as you know the Pythagorean theorem, you already have a trig identity. Right? So notice how this is a right angle triangle. Let's just use the Pythagorean theorem on it, right? A squared plus b squared equals c squared. That's going to give us cosine of theta squared plus sine of theta squared equals 1 squared. Now I'll go ahead and write this in a cleaner format. For future reference, if you ever have cosine, sine, tangent, any trig function squared, right, this is the way we want to write it. We put the 2 in between the cos and the theta. Right? Same thing with sine. This is just a better way or a cleaner way to write it. Right? But just by applying the Pythagorean theorem to this really simple thing, from the unit circle definition, we already have this really nice relationship. Cosine squared of theta plus sine squared of theta equals 1. And that's true for literally any angle. Right? Any theta, which is kind of mind-blowing, right? But it's true. It's true. And you also have some other trig identities that I kind of want to go over with you guys that kind of flow out of this identity that we literally just discovered. Right? So 1 plus tangent squared of theta. Is there any other form we could put this expression into? Well, let's think of what tangent is, right? So this is 1 plus tangent squared. Well, what is tangent? We said that tangent was sine over cosine, right? Okay. Well, sine over cosine squared, right? That squared is just going to apply to the numerator and the denominator. Right, so we could essentially turn it into that. And whenever you have a whole number plus a fraction, if you want to combine those two, you got to get them over the same denominator. So we could turn that 1 into cosine squared theta over cosine squared theta plus sine squared theta over cosine squared theta. All right, let's put these together. We have cosine squared theta plus sine squared theta over cosine squared theta. But notice what we have in the numerator, right? This thing right here, what did we say that was? That's equal to 1, right? That's just a trig identity. That's always true, no matter what the angle is. So really, this whole expression turns into 1 over cosine squared theta. Is there maybe a little bit of a simpler form that we could put even that in? Well, think about the reciprocal of cosine. We said that that was secant, right? Way up here. And so if that equals 1 over cosine squared, that's the same thing as secant squared. And that's the identity, right? So the identity is, just to summarize it, that 1 plus tangent squared theta equals secant squared theta. It's a really nice identity. And for this next one, I'm sure you can see it's kind of going in the same direction, right? So I'll go through this one a little bit quicker. Right? So that cotangent squared theta, that's cosine of theta over sine of theta squared. Then we convert the 1 into sine squared over sine squared theta, because I can see we're going to have to add some fractions, right? And we have over here cosine squared theta over sine squared theta, right? And then the same kind of thing happens, right? We have sine squared plus cosine squared. That makes the numerator 1. On the bottom, we have sine squared theta. Well, that's cosecant squared theta. So this identity says that 1 plus cotangent squared theta equals cosecant squared theta. Boom. So just by using the Pythagorean theorem and sort of manipulating some expressions, we actually got 2 more identities for free. And we're going to see a lot more where that came from. You might be wondering, why in the world are we learning about these identities? Why are they important? Well, essentially, the reason is, especially if you do calculus, that it's very often really helpful to have these identities to simplify expressions that are overly complicated. So, especially if you get into calculus and you're doing things like integrals or derivatives, it is so much nicer to work with something like this as opposed to maybe something like this in different cases, right? And so you want to be able to translate back and forth between the right side and the left side so that you can simplify your work and things like that. Right? So there are just situations where this is just really helpful for us to know. And let's go ahead and use these identities to just do really typical practice problem that you see often in trig. They'll say if, cosine or sine, in this case we have sine, is equal to 0.6. They want you to find everything else. And you might be wondering, well, hang on. We don't know what the angle is, right? It's just theta. What is the angle? Could be anything, right? But we still actually have enough information to solve this problem. So again, think back to that unit circle definition, right? And I'll just draw some generalized sort of line segment here. Here's my theta, right? And it creates that right triangle in the unit circle. We said that this was sine of theta, this was cosine of theta, this was 1. Right? And so if we know what sine of theta is, right, that tells us that this is 0.6. So really, just to sort of isolate just the triangle part, we know that the triangle has a hypotenuse of 1 and a height of 0.6. And the only thing we're missing is cosine of theta, right? We could call this, let's just call it x, right? If I want to find cosine, just use the Pythagorean theorem, right? So x squared plus 0.6 squared equals 1 squared. So that's x squared plus 0.36 equals 1. That means x squared equals 0.64. And at this point, you can probably tell that means that x equals, in this case, so normally when we take the square root of both sides, there would be a plus or minus, and then square root of 0.64, which in this case is going to be plus or minus 0.8. Now, it could be negative 0.8. That's actually possible. right? Because if you think about, again, the unit circle, you could have a very similar triangle over here with the same height of 0.6, but that goes 0.8 in the left direction, right? That's that green triangle I'm trying to draw there. For the sake of simplicity, let's just go ahead and assume that the black triangle is correct. Right. Usually they give you a little bit more information so that you can figure out which triangle is correct, but we'll go ahead and say that it is positive 0.8, right? So if I know that cosine of theta, let me scroll down, cosine of theta equals 0.8, I can find everything else, right? Because tangent of theta is sine over cosine, right? So that's 0.6 over 0.8. All right, we can simplify that a little bit. Let's see, that's going to be 3/4, or you could say 0.75. We got secant, right? Secant is 1 over cosine. We said cosine was 0.8. So that's going to be 10 over 8, which is 5 over 4. Or you could say 1.25. Cosecant, that's going to be 1 over 0.6. And that's 10 over 6, 5 over 3. Okay, so it's going to be something like 1.66 repeating. I'll go ahead and round it. All right, I shouldn't draw the bar. In fact, let me just go ahead and do this. Right, I'll draw the bar over the 6. That 6 is repeating. So that's cosecant, and then cotangent, right, is cosine over sine. So 0.8 over 0.6. That's going to be 4 over 3, which is 1.33 repeating, right? And so we found everything. So normally for these kinds of problems, they would say something like, they would probably have to give you a little bit of extra information so you can narrow down the numbers. They would say something like cosine of theta is positive, right? And that's what we would need to be absolutely certain that this is the right triangle, right? It's not the one that's reflected over the y-axis. So I think I left that out of the handout there. Okay. Let's keep going. If you want to pause, this would be a good time for any kind of brain break. If you need to maybe do another a unit circle quiz or just sort of look at something for a couple minutes, because we are about to get into some word problems. So make sure you're ready, you're focused. All right, so if you came back from your break, we're going to dive into some word problems. We have a surveyor is 115 feet from the Washington Monument and measures the angle of elevation to the top to be 78.3 degrees. How tall is the monument? So we will definitely need our calculators here. Unit circle ain't going to help us on this problem. So the Washington Monument, I think it looks something like this, right? It's just sort of a giant stick in the ground, basically. Let's draw a little background here. And this is our little surveyor. Right. For those of y'all who don't know what surveyors are, I actually know one. If you want to get into surveying, they usually have these like little tripod-looking devices that sort of figure out the level of the ground, the angles of elevation, and I mean, they can do all kinds of stuff. If you really want to get into that stuff, it pays pretty well. It's called GIS, and one of my friends is in that field. He does it right now in Washington, so pretty interesting stuff. But not a whole lot of people know how to get into it. So look at GIS. If you like making maps and things like that, GIS is probably for you. But anyway, this device that he's using is essentially measuring the angle, right? And they do it very, very accurately, right? So entire cities are based on GIS maps. And like if they want to go and build a mall or something, they're going to consult GIS people to survey the land. And I mean, it's really intense stuff. By angle of elevation to the top, what they mean is this angle right here. Right, so if I draw a horizontal line to the monument, and I draw a dashed line from my eyes to the top of the building, that is my angle of elevation. So that's going to be your 78.3. Let me redo that. 0.3 degrees. And I know that I'm a distance of 115 feet, and that's talking about that horizontal distance at the bottom there. So for any word problem, you always want to draw some kind of picture. Always. I mean, if you do not draw a picture, you will get confused. So I draw a picture every single time. Also, one other thing to keep in mind too is this angle is my theta, right? And so you also want to label your sides, right? So across, there's my opposite. Across from the right angle, that's my hypotenuse. And then this is my adjacent. So they gave me the adjacent side of this triangle, right? And so now, how tall is the monument? That's the opposite side. What is something that involves the opposite and the adjacent from SOHCAHTOA? Well, that's going to be tangent, right? Just write out SOHCAHTOA. Right, you got this part, this part, this part. The only part that involves O, which is what we want to find, right? And A is the TOA. This is what we're going to use. So tangent of 78.3 degrees is going to be our mystery distance, I'll put a question mark there, over 115 feet. And to solve for the mystery distance, even before you put this into the calculator, you can multiply both sides by 115 feet. So we have 115 times tangent of 78.3 degrees equals our mystery height. And now we can just calculate the left side to get the answer. All right, so I'm going to put this into my calculator. One really, really crucial thing you need to do at this point is, what type of angle am I dealing with? This is an angle in degrees, right? So you have to make sure your mode is in degree mode, which mine was in radian, so I got to change that. If your calculator is in radian mode and you decide to use it on this expression, you will get an answer, but it will be wrong, right? It has to correspond to the type of angle you have in the problem, right? So let's see, 115 times tangent of 78.3. That's going to give me an answer of 555.31 feet. And that is supposedly how tall the Washington Monument is. Cool beans. Let's move on. Here we got another problem. We have a skateboard ramp is created to make an angle of pi over 12 radians with the ground. It has a horizontal distance of 13 feet. Find the length of the ramp and the height. Okay. One thing to clarify too, I might have not been clear about this. The length of the ramp is talking about sort of the slant, right? The slanted part of the ramp that the skateboard is actually going to ride on top of. Right? So let's draw a picture of this. Also notice pi over 12, that's a really small angle. I mean, on the unit circle, we have pi over 6. Pi over 12 is half that size, right? So our picture is going to be pretty... We're going to have a triangle with a really skinny angle there. Right, that's sort of my ramp. So this is a very shallow ramp. It's pi over 12. There's my right angle. All right. We also know that the horizontal distance is 13 feet, right? So that's this distance here. And they want us to find the length of the ramp. So I'll call this L, right? That's my length here. And the height, right? This is my height. So I want to find H and L. Okay, another thing to point out here too. Let's go ahead and figure out our opposite, adjacent, hypotenuse, right? So the side length of L is our hypotenuse, right? This is our H, that side. This is my angle, so across from that is my opposite, and then the last remaining side is my adjacent. So in this case, they gave me the adjacent, right? Okay, so if I want to find, let's say we start with L, right? Well, we're given A, so we're given the adjacent side, and we're trying to find H. Right, write out SOHCAHTOA. Which part of SOHCAHTOA do we got to use? Well, that's going to be the K in SOHCAHTOA, right? It's got the A and the H. It's going to be a cosine. So cosine of pi over 12 equals 13 over L. And by a similar thing that we did in the last problem, well, it's a little bit different here. Notice how the L is in the denominator. We could essentially multiply both sides by L and then divide both sides by cosine of pi over 12. So let me do that in slow motion here. So we would get to something like this, equals 13. And then if you divide both sides by cosine of pi over 12, we get that L equals 13 divided by cosine of pi over 12. Right, and now we can calculate the answer with the calculator. Let me also set up H as well. So I'm going to save all the calculator stuff for the end. I'm just going to simplify as much as I can. Let's do this in a different color. The H is my opposite side. And I'm going to go ahead and use my adjacent again, right? Because we know it's exactly 13 feet, which is really, it's good to work with exact numbers instead of approximations. Well, that's my O and my A. That's the TOA part, right? So we're using tangent here. Right, so that's going to be H over 13. And this one, just multiply both sides by 13, and we'll get that H equals 13 times tangent of pi over 12. And so we'll get both dimensions of the ramp. Now, if you just go based on an intuitive gut feeling, right, we would expect that H is going to be a very small distance, right? We would also expect that L is going to be a little bit bigger than 13. So these are things that you want to keep in the back of your head so that if your calculator is in the wrong mode, you'll be able to spot it. But in this case, our angle is definitely in radians. Let's change to that, go to mode, and click on radian. Now that we have it all set up, I'll just put it in. So 13 divided by cosine of pi over 12. That's going to be, it looks like 13.46. And that's going to be, it looks like, what, feet. Gotta have units. Yeah, and it's a little bit longer than the horizontal distance, right? That's what we expect. This one should be pretty tiny, right? So 13 times tan of pi over 12. Yeah, this is 3.48 feet. Bingo. Right, so it's a very shallow ramp here. And I'll go ahead and jump to this last one. I'll leave the extra probably for you guys to think about. Maybe I'll get to it. I don't know. Let's see. So I've drawn a little picture for this one because I wanted to clarify what it's talking about. We got a lighthouse that is 200 yards from the bike path. So by 200 yards from the path, obviously this path is all over the place. Like, are we talking about here? I just wanted to clarify it's the shortest distance to the bike path. That's 200 yards. I got this from the textbook. So a walkway to the lighthouse is 400 yards long, right? So this is my walkway. So this is just a walkway. It's kind of a longer distance from the path to the lighthouse. And they want us to find the acute angle between the bike path and the walkway. So we've got the bike path here. It's this thing. The walkway is here. Right, this thing over here is the walkway. Right, and so the angle that they make is going to be right here. So they want us to find this angle right there. Okay, well, let's first figure out what they've given us, right? So there's my angle. I know that this is a 90-degree angle because it's the shortest distance to the path, right? So that purple line is going to make 90-degree angles. You can prove that to yourself if you think back to like geometry stuff. Right? But if this is my 90, right, it's looking across at the hypotenuse, which is over here. If this is my angle, that's looking across to the opposite side. And then I got my adjacent. Okay, so they gave us the opposite and the hypotenuse. Now let's look at SOHCAHTOA again. Which one are we going to use, the SO, the CA, or the TOA? Well, they gave us O and H, right? So that's the SO part. That tells me that sine of this mystery angle equals 200 over 400 yards. I guess I should put the yards there. Notice that the yards essentially cancel out in this calculation, right? Because sine is really, it's not spitting out a distance or anything that you can measure. It's spitting out a ratio as the output, so it shouldn't have any units. But what is this? This is 1/2. Well, think back to your unit circle, right? What values on the unit circle, what angles cause sine to spit out 1/2? Well, there's only 2, right? And notice how they told us an acute angle, right? So that's going to be a key. If you draw a unit circle, it's a terrible circle. There's really only 2 options. You either have a triangle going out like this, or you have a triangle going out like this. All right, we said that the shorter side of these 30, 60, 90 triangles in the unit circle is always 1/2. And it's not going to be any of the triangles on the bottom, right? Because the y-coordinate for the ones on the bottom are negative, right? The answer should be a positive 1/2, right? So it's only either one of those 2. And remember, the angle measured on the unit circle is from standard position. So we have this angle, right? This is a theta. And then in a different color, I'll say that from here to here is another angle theta. Now, if they told us it's an acute angle, it's got to be the orange one, right? So what is that angle? Again, this is just something you should know from the unit circle. That's theta equals 30 degrees. Or you could say pi over 6 radians, right? So that's something you should know. You should know this from the unit circle. And again, if you don't know that, you need to keep practicing, right? All right, well, you know what? I'll go ahead and tackle this extra part. So suppose you have a triangle where the hypotenuse is twice as long as the adjacent side. All right, so imagine, let's see, let's draw a triangle, I guess like this. And let's say my angle is here. In fact, this argument should work no matter where you draw the angle. So my adjacent side is over here. Here's my hypotenuse. Here's my opposite. The only thing I know is that the hypotenuse is twice as long as the adjacent. They don't give me any numbers whatsoever. And so you might think, well, we can't do anything. Well, actually we can, right? Because remember, with sine, cosine, and tangent, it's the ratios that matter. The ratios matter. So let's say that my adjacent side is, well, you could choose any number for it, or you could choose a variable, right? I might choose, let's say 10. That means my hypotenuse needs to be 20. Oh, look at that. I have A and H. Let's use SOHCAHTOA again, right? That's the K in SOHCAHTOA, right? So that tells me that cosine of theta equals 10 over 20, which is 1/2. Again, this is a unit circle value. What angle does this value correspond to? Well, let's assume that the angle is acute again, right? This would correspond to an angle, again, this is for cosine, the angle must be 60 degrees. Let's say that theta is acute. I should have specified that. So the angle is 60 degrees. Cosine of 60 degrees gives you 1/2. If theta is 60 degrees, then sine of theta is sine of 60 degrees, which is, again, if you know your unit circle, this is radical 3/2. Bingo. That's the answer. So hopefully this helped. With these kind of problems, I highly, highly, highly recommend that, number one, you make sure you're in the right mode. Number two, you draw a picture of some kind. You gotta draw a picture of that triangle somehow. And then number three, I always label the three sides. So hypotenuse, then label the opposite, then label the adjacent. Right. And from that point on, you just need to use SOHCAHTOA, use the numbers they give you to find something that you don't know. Right. And that's really, as far as a recipe goes, or a step-by-step process, that's how I do every single one of these. I draw the picture, label the triangle, make sure I'm in the right mode, and use what you do know to find what you don't know. So anyway, take care. Have a good weekend, guys. Hopefully this helped.